Success is to be measured not so much by the position that one has reached in life as by the obstacles which he has overcome. Legendary educator Booker T. Washington placed imagination and determination to overcome challenges at a higher pedestal. Truly, mathematical innovations to overcome the twin challenges of the division by near zero as required by the rate formula and the physical measurement of change during near zero time. Over 300 years ago, tower well above the significance of calculus in the 21st century. Recall the lesson on motion. It talked about the three major challenges in computing the instantaneous rate of change, exemplified by the rate of change of motion. The three are: first, how to accurately measure the rate of change in an instant of time. In the case of motion, it is measuring speed at any definite time at a near zero duration of time. Second, how to quantify or numericalize that instant of time. That is, what is that non-zero duration of time that is almost as good as zero for the thing that is changing. Third, how to be sure that the chosen quantity of the non-zero instant is relevantly small enough to ensure to get us an unchanging rate of change for that instant. It should not be that the rate of change varies in the chosen quantity of instant. The third challenge is very interesting, that of avoiding any chance of the chosen instant representing more than one instantaneous rate of change. For example, if speed, the rate of change of distance in any motion, has more than one distinct values in that instant, then there is no instantaneous speed. Instantaneous speed or rate of change is expected to be just one unique value for that instant. That is the very definition of what may happen in an instant. The whole point of any measurement in an instant is to find the target quantity at the very instant it is planned. Two situations are easily visualizable wherein the rate of change, that is speed, may change in the chosen quantity of instant, when the instant is bigger than necessary to measure the instant rate, and when the instant is such that it is the point of a sharp shift in the rate of change. Let us briefly explore how calculus overcomes these three challenges in measuring rate of change. Obviously, overcoming the challenges must also ensure that we are able to detect any instant that is bigger than necessary, or any sharp change in the rate in the instant of measurement. We can restate the challenges in computing instantaneous speed as rate in three discrete categories. First, the physical challenge. This is about the impossible task of measuring rate of change in near zero instants. Second, the mathematical challenge. This is about the challenge of actually choosing the near zero number for the instant that are same as being zero in the context of the changing quantity. Third, the conceptual challenge. This is about ensuring that the chosen quantity of the instant is such that the rate of change at that instant is truly singular, accurate. Let us also explore how calculus resolves these challenges. Physical challenge and its resolution in calculus. We will exemplify it in the context of motion. Recall, physically it is near impossible to correctly record the rate of change, such as speed, in a very small amount of time, called the infinitesimal time. The innovation that overcame this challenge was using the idea of an indirect quantity, a derived quantity, called the derivative. Thus, speed is not computed directly, it is mathematically derived. Please hold on for how it happens. The mathematical challenge and its resolution. The idea of limit. Mathematically, selecting the right infinitesimal number as the value of the instant is a challenge. It has to be quantitatively appropriate to be instant for the given changing quantity. Calculus overcame this challenge by introducing the idea of limit. Limit mathematized the quantity of instant. The instant time is no longer physically used. Limit took the battle of finding the instant that is small enough, infinitesimal, from real to analytical. And how did this happen? How does limit work? Functions were made the medium of working with limits. We made continuously changing quantities be mathematically expressed as function. We use functions to find the rate of change at any instant, all mathematically, using equations. And all the while being able to get the right quantity of the instant that we must have. The limitations of the limit, as must be expected in any innovation, was addressed through the idea of continuity assurance or checks. It is discussed next. Limit is a significant example of how mathematics frees us from the limitation of the physical measures of time or anything else, just as addition, for instance, frees us from actually counting things for quantification. The use of limit, in place of finding the instant quantity, hijacked the task of finding the instantaneous rate of change onto a very different trajectory, a totally novel way of measuring change in any quantity, including the rate of its change. Limit introduced an inventive way of representing, describing, expressing the whole of motion itself and other changing situations. It used equation, kind of mathematical equivalent of real changing situations, called functions. And the functions would give the changing quantity of things without involving any physical measures. For example, the distance traveled does not require any physical measurement, and thus, the rate of change of distance and speed also does not require any physical measurement. When finding rate using limit, there was no need of quantifying the chosen instant. We could find distance, speed, acceleration, etc. for any motion without physical measurement. It was a mathematical solution for a mathematical challenge. Limit took the battle of finding the instant that is small enough, infinitesimal, from real to analytical. And how did this happen? How does limit work? Functions were made the medium of working with limits. We made continuously changing quantities be mathematically expressed as function. We use functions to find the rate of change at any instant, all mathematically, using equations, and all the while being able to get the right quantity of the instant that we must have. The limitations of the limit, as must be expected in any innovation, was addressed through the idea of continuity assurance or checks. It is discussed next. Conceptual challenge and its resolution, the continuity of the limit. Conceptually, when using limit, there is the issue of the verifying or assuring that the limit instant represents one rate of change. The rate is not changing during the instant. How is this ensured? Recall, limit is implemented through functions. That is, the instantaneous rate of change is computed not through any measurement but analytical means, mathematical equations. And the functions also help us ensure that the derived rate of change is truly for the instant it is supposed to be of, and it is the only rate in that instant. For limit to be valid, thus, the rate of change at the instant where limit is applied, the function must be continuous. A function is said to be continuous at an instant if the value of the function exists at that instant, and that value of the function is same as the value of function immediately before and after that instant. And how do we measure the continuity at an instant? We will soon explore in the slopes of the functions. In a way, the validity of the rate of change computed using limit at any instant is dependent on that rate of change being the same immediately before and after that instant. Expectedly, continuity becomes a critical complement of the application of limit in finding the rate of change of something at any instant. Indeed, limit and continuity are used together. The rate of change computed using limit is checked for being the only rate of change at the instant by applying the test of continuity on the function at that instant. Continuity is a conceptual breakthrough. It uses the values of the function very close to the instant, not the instant, to give us the rate of change. It is independent idea too, in itself a concept on the behavior of functions, their curves. It stands for functions checked for being without abrupt jumps, laying the foundation of calculus and the analysis of functions of real and complex numbers. It had a transformative impact on how we model the world around us. It must now be easy to realize where the name continuity comes from. The name reflects what it does. It helps us check if a computed rate of change around the instant, but very close to it, continues to be the same as that of the instant. It is the mathematical means of securing that a rate of change does not change during the instant. And how do we measure the continuity at an instant? We will soon explore in the slopes of the functions. Continuity is a masterstroke in analytical quantification, virtual measurements. Continuity helps us effectively use infinitesimal instant values and make sense of the value of the limit of the function and points very, very close to it. It is to capture any sharp variation in the rate as the infinitesimal time around the instant becomes smaller and comes closest to the value of the instant. It is obvious that continuity is of interest at the instant of interest, and thus it is tested for slope as close to the instant as possible. Any detected sharp variation declares a lack of continuity at that point, and that would mean the limit of the function at that instant is not same as the limit of the function just before and after the instant. Thus, the rate of change computed at that instant is not constant around the instant. That rate cannot be taken to be solely duly valid at that instant. It is obvious that continuity is of interest at the instant of interest, and thus it is tested for slope as close to the instant as possible. Any detected sharp variation in the slope around the instant declares a lack of continuity at that point. And that would mean the limit of the function at that instant is not same as the limit of the function just before and after the instant. Thus, the rate of change computed at that instant will also not be constant around the instant. That rate cannot be taken to be solely duly valid at that instant. Together, they are the force that is calculus. The importance of continuity. A note. Let us just roll back a bit and recap limit and continuity, the two innovative concepts. When we say the limit of a function exists at a point or instant, we mean that as the value of the function around that instant is as expected, close to the value of the function at that point. Thus, when limit exists, the slope of the tangent and the curve is the same. The curve can be assumed to be a straight line around that instant. Thus, the idea of limit introduced a way of having an infinitesimal instant when the slope of curve is same as the slope of the tangent. Interestingly, limit solved one big problem, but left us with another. It helped us get the slope, or rate of change of a function at an instant, to be the slope of the curve itself. But the new problem was how to compute and relate the three quantities around the instant: left-hand limit, right-hand limit, and the value of the function at that instant. It increased the computations. The concept of continuity helps us understand and identify points of discontinuity in a function. Thereby, we do not have to necessarily and specifically compute the left-hand limit and the right-hand limit. In effect, we find limit of a function at an instant or point and the rate of its change at an instant without worrying about the left and the right limits. We just check for the discontinuities of the function, and even that is easily seen when functions are graphed. We can see jump in value of functions, sharp turn at a point, or a whole or undefined value of function at a point in a graph. Let us briefly connect to functions and how it is the vehicle of innovations that limit and continuity are. Function is the gateway to the instantaneous world. We functionalize everyday situations to precisely capture the changing nature of the relationships embedded in such situations. Functions are particularly relevant for continuous change. We work with functions alone. Limit, continuity, derivatives, and more are just work on functions. No physical and actual measurements are needed. An example of how functions are a critical part of technology and engineering. We use functions to convert the harsh physical changes, that is, real changes, to completely virtual changes. For example, the impact of a car crash on the head and neck of human passengers cannot be tested in real. We create functions for the physical and biological conditions of the neck and head and take it through different sets of data, that is, conditions, to test the changes. Measurement challenges in continuous motion are resolved by calculus. Calculus overcomes these challenges by completely negating the need for physical measures. The ideas of derivative, functions, limit, and continuity do the trick. Indeed, the idea of calculus is simple. It is mathematization of physical changes. Over the next lessons, derivatives, functions, limit, and continuity are briefly but exclusively explored conceptually. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.